This video is going to be the beginning of an endeavor which the vast majority of academic philosophers have considered deeply taboo for now more than a century. An attempt to reconcile our physical understanding of nature with metaphysics more generally. This is an endeavor which will involve a great deal of speculation and will involve questioning many of the inferential claims which have come to be regarded as established facts within the academic study of physics. My aim here is to piece together a conceptually coherent understanding of the physical world, one which adequately accounts for phenomena which are actually observable. In doing so, we must be very attentive to the distinction between phenomena which are actually observable and those which have been established, as it is said, through theoretical inferences. Within any scientific endeavor, we must attend to the dangers of what Alfred North Whitehead termed misplaced concreteness, our tendency to reify our conceptual abstractions as though such models were in fact nature itself. Our tendency, in other words, to mistake maps for territories. Physics is, of course, an absolutely enormous field of study, and what I'm going to be presenting here is, above all else, a work in progress. Adequately reinterpreting and recontextualizing every known physical phenomenon is far beyond the scope of what one theorist, let alone one series of YouTube videos, can hope to accomplish. Nonetheless, this is a project which I have increasingly come to see as absolutely necessary. The depiction of the physical world which we are presented with by academic physics is, as we shall see, utterly rife with ontological incoherences, which simply cannot be ameliorated by exotic mathematical objects, dark particles, superstrings, additional dimensions of time, or any of the other unobservable and fantastical phenomena which have been postulated since physics entered its crisis phase during the mid-20th century. Our first order of business, then, must be an understanding why engagement between physics and metaphysics has become a taboo in the first place, as understanding the origins and nature of this zeitgeist will allow us to see much more clearly the traps which have been laid out before us, consciously or otherwise. Within modern academic physics, it is now an unspoken yet deeply entrenched presumption that the maps produced by academic physics are, in fact, the territories in question, that mathematical equations are somehow the engines which actually drive nature itself by juridically commanding actual entities in the world to behave in certain ways. Insofar as this presumption holds, it then follows that metaphysics should have no business in saying anything about the science of physics. Physics can remain insulated away from any and all serious criticism by this ideological conviction that physical theories need only be mathematically sound and have no obligation to actually provide us with a genuine, cohesive understanding of why and how the physical world is the way that it is. Prediction and technological application come to replace genuine knowledge. In attempting to understand where we must go, we must first understand where we are, and this of course means that we must understand the path which has brought us to our present situation. For most of the history of physics, we see a common understanding that the study of physics was in fact a subfield of metaphysics. Isaac Newton was not simply a mathematician who strove to create mathematical models which could predict empirical observations. Newton was a metaphysician who very explicitly saw his physical theories as an extension of the study of metaphysics more generally. Isaac Newton and many other such physicists before and after understood that an actual understanding of the physical world was necessarily contextualized within a broader understanding of the nature of reality as such. The notion that physics could be quarantined within an impenetrable fortress away from philosophy, and by extension away from all other fields of science, would have been seen as unthinkably absurd. In order to do physics at all presupposes a conceptually coherent understanding of what physicality itself actually is, and what the compositional architecture of the natural world must be. To do physics, therefore, was inextricably a matter of doing metaphysics. Within the opening decades of the 20th century, however, this understanding of the role of physics within the context of natural philosophy would come to rapidly shift. We can see early developments of this process and the unfolding of its implications within the public debates of 1922 between the physicist Albert Einstein and the philosopher Henri Bergson. The story here begins with the infamous Michelson-Morley experiments, which attempted to measure the effects of the motion of the Earth through the hypothesized luminiferous ether by studying the theorized effects of this motion on the propagation of light. First conducted in 1887 by the American physicists Albert Michelson and Edward Morley, this experimental setup involved reflecting perpendicular beams of light which were then recombined. During this time period, it was widely presumed that the propagation of light was mediated through what was known as the luminiferous ether. The ether was presumed to be a kind of static electromagnetic background through which electromagnetic waves propagated through pressure mediation, much like sound waves or ocean waves. If this etheric background was indeed static, that is, stationary in relation to the Earth's movement through it, then the beams of light which moved against the Earth's trajectory through the ether would presumably propagate faster than those which moved concurrently with this relative motion due to a kind of drag effect. The Michelson-Morley experiment was intended to detect this drag and thereby allow for measurement of the relative motions of the Earth and the ether by detecting interference patterns within the beams of light which would be affected by this relative motion. Surprisingly, however, the Michelson-Morley experiments produced only null results. There was no such interference pattern, and this null result proved to be immensely difficult to explain. One possible explanation was provided by the Dutch physicist Hendrik Lorentz, who proposed that there was a physical length contraction which occurred due to the motion of objects in relation to the ether. Physical distances themselves would contract by a very minuscule amount, such that the speed of light was measured as being constant, regardless of its path through the ether. The problem with this explanation, however, is that it seemed immensely ad hoc. There didn't seem to be any sensible reason why nature would seemingly go out of its way to contract physical distances in order to maintain the constancy of the measured speed of light. As such, many sought a more cohesive explanation, largely due to the fact that this problem emerged during a time before physics abandoned the idea that sensible explanations were good explanations. Though, as we shall see, this problem was also the beginning of a trajectory through which physics would ultimately abandon the idea that it was obligated to actually explain anything at all. Following this infamous null result and the general dissatisfaction with the Lorentzian explanation, Albert Einstein would propose his special theory of relativity in 1905. Much like the Lorentzian explanation, the Einsteinian explanation also postulated the contraction of space, as well as the dilation of time, in order to explain the null result of the Michelson-Morley experiment. The difference, however, was that Einstein's explanation involved no reference to an etheric medium whatsoever. Special relativity conjectures that there is in fact no absolute static background of space, time, or ether, and instead relativizes both time and space through an absolutizing of light speed. In order to adequately understand the significance of this conjecture and its implications, we must contextualize special relativity in relation to the overall history of Western physics. Prior to the development of special relativity, Isaac Newton's theories of motion, gravitation, and optics had remained foundational to the study of physics for well over 300 years. What is often overlooked in discussions of Newtonian mechanics, however, is the fact that Newton's theories inalterably require the metaphysical presumption of an absolute spatial background. And here we must understand exactly why. When we think intuitively about the notion of rest, we tend to think in terms of stationary objects. An object is at rest if it is not moving, and in order for something to move, some sort of force must be involved to compel such motion. Isaac Newton's most ingenious conceptual revision was a generalization of this notion of rest. Newton conjectured that, contrary to our intuitions, resting states needn't necessarily be stationary states. Rather, Newton tells us that a straight line trajectory through space with a constant velocity can be a kind of resting trajectory, as it were. Objects in motion will remain in motion unless acted upon by an external force. It was specifically through this conceptual revision that Newton was able to develop theories of motion that were able to account for both the behaviors of physical bodies within the terrestrial world, as well as the motions of celestial objects within the heavens, thereby effectively coming to complete Galileo and Kepler's philosophical project of expanding the domain of scientific inquiry to encompass both the heavenly realm as well as the earthly. Rather than conceptualizing the astronomical domain as a transcendental realm which resided in contrast to the natural world, as the Platonists had done, there was now only nature. And such thinkers had thus come to be compelled by the belief that the constants at work within the earthly realm were the same constants at work within the heavens. Newton's reconceptualization of rest and inertia allowed for the development of theories which seemed to affirm and complete this philosophical project. But Newton's theories necessarily required an absolute notion of space. Newtonian mechanics requires that the motion of an object be ontologically definite. There needed to be a very real, objective truth as to whether an object was in fact stationary, moving at a constant velocity, or accelerating. If we remove this implied Cartesian spatial grid from the background, then all motion becomes merely relative motion, and Newton's theories simply break down. Imagine a star and a single tiny planet orbiting the star. If we presume that there is an absolute spatial background, then we can presume the star to be at rest, or at least to be moving in a constant resting trajectory. We can then view the planet as in motion around the star. We can compare the implicit straight line trajectory which the planet's inertia is trying to achieve with the force of the star's gravity acting upon the planet. The planet is trying to move in a straight line, which is its resting trajectory, but the star's gravity curves that trajectory such that the planet moves in an elliptical path around the star. If we remove the implied spatial background from this scenario, however, then this would mean that there simply is no objective reality as to whether the star or the planet is stationary. We could just as easily regard the planet as being stationary, with the star moving around the planet. But when we attempt to analyze this scenario in a Newtonian fashion, the model stops working. The gravity exerted by the planet must somehow pull the star's implied straight-line resting trajectory into an elliptical orbit around the planet. But the planet does not have enough gravitational influence in relation to the star's mass in order to do so. More generally, we can see that without a static spatial background, terms like motion or rest, and by extension, acceleration and gravitation, cannot be coherently defined in Newtonian terms. If there is no objective truth regarding whether or not an object is actually at rest or accelerating, then there can be no objective truth as to whether the forces acting on an object are actually following Newtonian principles or not. Many modern commentators will casually claim that Newton's laws of motion and gravitation do not require an absolute spatial background, even though Newton himself did believe in such a background. But this is very misleading. Newton's equations can be used practically within the terrestrial realm or within our solar system because we can implicitly treat the Earth or the Sun as though they were at a state of absolute rest that the motion of other bodies can be defined in relation to. But this treatment presumes that these Newtonian models are in fact approximations of the presumably more veritable Einsteinian models, which can justify such an as-if treatment. Taken in themselves without an absolute spatial background, Newton's explanations do not work. But the notion of relativity was also not a novel development in the Einsteinian era, nor in the Newtonian. Prior to the development of Newtonian mechanics, Galileo had suggested the notion of relative motion and mechanical invariance. Galileo asks us to imagine that we are on a ship traveling at a constant velocity across the sea. Assume that you are within the hull of the ship but don't realize that the ship is in motion. It is moving at a constant velocity and therefore you experience no acceleration. If you then take a ball and throw it across the hull, it will travel, bounce, and come back to you just the same as it would if the ship were stationary relative to the Earth. We can thus infer that there is a kind of invariance with regards to physical mechanics, unless acceleration is involved. The mechanical principles operate the exact same way, provided that there is an objective reality to acceleration. If there is no objective truth as to whether or not an object is actually accelerating, then there is no way to discern whether or not the physical mechanics will actually be invariant or not. On Earth, acceleration can be defined in relation to the Earth. Galileo's ship is either accelerating or not in relation to the Earth's gravitational influence, which we can regard as being stationary. If we fully relativize space, however, then acceleration becomes undefinable, and these notions of mechanical invariance conceptually fall to pieces. Imagine, for example, that you were in a spacecraft which accidentally fell into a wormhole that spat you out into a parallel universe that was completely empty. There is literally nothing within this universe other than empty space and your spacecraft. So, in this scenario, is your spacecraft moving or not? If there is no absolute space, then there is no way to know because there simply is no objective reality as to whether you are actually in motion or not. Here we must be very clear. The issue at hand is not that we cannot know the velocity or acceleration of your spacecraft because there are no other objects in this universe to compare this motion in relation to. The issue, if there is in fact no absolute space, is that there is not any objective truth regarding your motion or lack thereof. So then we must ask, will you experience any acceleration in this scenario? We could of course presume that since motion cannot be defined, you will not experience any acceleration, but what if this spontaneously changed? Imagine that several hundred light years away, a star suddenly blinks into this new universe, having fallen through a wormhole just as your ship had done. Now, suddenly your relative motion can be defined. If the star's relative motion in relation to your own is accelerative, will you suddenly feel the jolt of acceleration as this universe suddenly realizes that it has a way to define your acceleration? Perhaps it would take several hundred years for your ship to realize that it is accelerating due to the limitations of light speed. But then, how does this universe decide whether you or the star is the one accelerating? Perhaps you could say that because your spacecraft's thrusters are operating, then this means that you must be the one accelerating, not the star. But mightn't it also be the case that some external force is attempting to move both you and the star, and that your thrusters are just resisting this force? How would the atoms which make up your craft be able to determine whether or not they are accelerating? How would they know whether to maintain mechanical invariance or not? Again, we must keep in mind that this seeming paradox is not due to a lack of information. It's not that we don't know whether some unseen force is attempting to move the ship and the star, with the ship's thrusters resisting this force. The problem is that there is no objective reality to the question as to whether that is the case, in contrast to the possibility that the ship is indeed accelerating. The laws of physics within this universe have no way to know, as it were, because there is nothing to know. There is no way to objectively define the difference between the two scenarios, and as such, no way that this universe can decide, as it were, whether to treat you or the star as the accelerating body. This is, of course, a rather fantastical thought experiment, but imagine scenarios such as these can allow us to achieve a broader view of the conceptual problems which lie within such physical models. I am not, of course, suggesting that the questions raised by this thought experiment do not have answers, but it is how we go about attempting to resolve these seeming paradoxes which is at issue here. The notion of absolute space allows us to avoid these problems by positing that there is in fact an objectively definite reality to motion, not just relative motion. Then we could say that even in an empty universe, your spacecraft will experience acceleration depending upon whether its velocity is actually changing in relation to the static spatial background or not. But then we must ask, what might actually constitute such a background? Even in the age of Newton, absolute space was not without its critics. Gottfried Leibniz, for example, had argued that space was in fact an entirely relational phenomenon. Space, Leibniz argued, was not in itself ontologically substantive, but was rather an abstraction which ultimately referred only to relationships between the geometric properties of actual objects. In other words, we could regard the location of an object as being the xyz coordinate properties of the object, which are defined only in relation to other objects. The values which we assign to those xyz properties of the object are only quantifiable insofar as we arbitrarily define some object as the bearer of the origin point, as these properties are relationships between the object and other objects. In many ways, this relativistic interpretation of space seems more appealing, as it doesn't require us to presume an unobservable absolute background or to regard space as an entity with its own coordinate properties. If we posit such an absolute background, then it seems that there must be some very real origin point in the universe such that absolute rest or motion can be defined in relation to it. In other words, there must be an actual center of the universe somewhere. The problem, however, is that if rest and motion are relativized in this manner, then so is acceleration, and the invariance principles of physics lose their coherence. With the advent of electrodynamics in the 19th century, this notion of an absolute spatial background would transform into the notion of the luminiferous ether, which was said to be the medium of electromagnetic propagation, as well as the static frame which kinetic properties could be defined in relation to. The ether provided a way for absolute motion and acceleration to be defined without the need for a notion of a cosmic origin point, and thus seemed to resolve many of the issues above. But if this hypothetical ether was indeed a static, motionless background, then that possibility would carry with it empirical implications. The Michelson-Morley experiment seemed to show that nature did not, in fact, accord with the predictions of the ether hypothesis. Einstein's special theory of relativity, or STR, then seemed like a way that physics could do away with the problematic notions of absolute space and the luminiferous ether by rendering light itself as the arbiter of invariance. Special relativity tells us that the speed of light through empty space is invariant with regards to all inertial reference frames. The speed of light will thus appear to be constant, while space and time themselves contract or dilate in order to preserve this constancy. As Einstein soared to popularity in the wake of special relativity, he was not without his critics, however. One of those was the British metaphysician and pioneer of mathematical logic, Alfred North Whitehead, who saw Einstein's theories as having implications that were as profound as they were utterly unacceptable epistemologically. This is a notion which we will be returning to later on, but for now we will mostly be focusing on the criticisms of relativity which were brought forward by the French mathematician and philosopher Henri Bergson. In his critiques of special relativity, Bergson did not argue that Einstein's math was wrong, that he had misunderstood the implications of the Michelson-Morley experiment, or that the dilation of time was physically impossible. Rather, Bergson's critique was in many ways far simpler and far more crucial. According to Bergson, the fundamental issue with special relativity was that Einstein himself was failing to adequately or consistently understand the implications of his own theory. Imagine that you are standing in a field between two clocks, which are positioned some distance away on either side of you. These clocks are designed to stop if a lightning bolt strikes the ground near them. As it just so happens, 2 lightning bolts strike the ground near each clock and both stop at exactly 12 o'clock. From your perspective, these 2 lightning strikes were simultaneous, and your clocks would seem to accurately reflect this reality. But now suppose that another person is in the exact same scenario. They find themselves in a field between 2 clocks, which are set to stop upon detecting a nearby lightning strike. Unbeknownst to this second observer, however, the field that they are standing on is actually situated on top of a giant airship that is moving relative to your position down on Earth. Because the second observer is in motion, time dilation effects will come into play. From your perspective, back down on Earth, it will appear that the second observer's clocks are out of sync with one another. The clock which is posterior to their motion will seem to lag behind the one which is anterior to their motion due to time dilation. Yet, from the second observer's perspective, their clocks will appear to be perfectly synchronized. But it is here that we must apply the concept of relativistic symmetry. If there is no objectively definable sense of being stationary, then it is equally true to say that the second observer in the airship is stationary, and that you are the one in motion. Perhaps the second observer's airship is traveling at exactly the speed of the Earth's rotation. The second observer will look at your clocks and see them as out of sync with one another. You could protest that you are stationary and that their clocks are actually the ones which are out of sync due to STR's time dilation, but the second observer could claim that they are the one who is stationary, and that you are moving because you are being dragged along by the Earth's rotation. The reality, according to special relativity, is that neither observer is correct because there is simply nothing to be correct about. There is no objectively stationary rest frame, and therefore the claim that you are stationary is just as true, or rather just as meaningless, as the claim that the second observer is stationary. You will observe the lightning strikes on either side of you as simultaneous, and you will perceive those of the second observer to be divided by a slight time lag. The second observer will perceive their own lightning strikes as simultaneous, and yours as divided by a time lag. What special relativity would seem to imply then is that both of you are wrong in the sense that there simply is no such thing as objective simultaneity. Now you might be thinking that you and the other observer could simply bring your clocks together to see whose clocks are actually in sync. So you get on a plane and fly to their airship in order to show them that your clocks are in sync after all. But once you arrive, you realize that your clocks are now out of sync due to the fact that you are no longer in the same inertial reference frame. If the second observer comes down to Earth to compare his clocks with yours, then the inverse scenario will occur. There is simply no way to determine whose clocks are actually in sync, as synchronization itself can only be understood in relation to a given frame of reference. Henri Bergson, however, argued that the most central factor here was in the inherent symmetry implied by relativizing these effects. Because of the reciprocity of these theoretical measurement effects, one cannot claim that these effects are actually real in any physical, objective sense. One of the major appeals of special relativity was that, unlike Lorentzian length contraction, the complete relativization within STR implied that there was no actual length contraction. Rather, such contraction and its correlative time dilation were to be taken as distortions of measurement, not as ontological effects. As such, special relativity cannot explain any ontological, concrete phenomena, and it is here that we can begin to see the inner incoherence of the Einsteinian framework. Special relativity, and by extension, general relativity, must regard these dilation and contraction effects as ontological, objectively real physical effects in order to explain empirical phenomena. But in order to do so, one must ignore the inherent reciprocity or symmetry of these theories, and thus quietly implicate the very same absolute background of space and time which Einstein aspired to annul. One example of this is the effect of time dilation on the decay rate of muons. Muons are quantum entities which very rapidly decay after being created. When muons are traveling at very high velocities, however, we observe that their decay rate is lengthened. The muons actually exist for longer periods of time when moving at relativistic speeds, and this is explained as being due to the time dilation effects of special relativity. What special relativity would seem to imply, however, is that from the muon's own frame of reference, no such time dilation actually occurs. No matter what the muon's velocity is in relation to the Earth, there is still no privileged frame of reference. The muon can declare itself to be stationary and the Earth to be in motion, and that all discrepancies regarding time are due to the motion of the Earth, not the muon. So, suppose we accelerate a muon at very high velocity towards a detector which is connected to a bell. If the muon were to undergo no time dilation effects, as would be the case from the muon's own reference frame, then the muon would decay before it reached the detector, and the detector would not be activated. The bell will not ring. From a stationary position on the Earth's surface, however, the muon will appear to undergo time dilation as a result of its relative velocity. Neither the position on the Earth's surface nor the trajectory of the high-velocity muon can be regarded as truly stationary or truly in motion, as special relativity has completely relativized both space and time. So now we must ask, does the muon actually activate the detector and ring the bell? If we attempt to interpret this time dilation as a real, physical effect, then we encounter a paradox. From our perspective, the muon will appear to decay more slowly and will thus reach the detector and ring the bell. From the muon's perspective, however, there will be no such time dilation, as its frame of reference will be an effective resting state from its own perspective. It will decay at a normal rate and will not reach the bell. We are forced to conclude that somehow the bell will both ring and not ring, depending upon which reference frame we are arbitrarily privileging. So at this point, the defenders of relativity will invoke length contraction in order to resolve this paradox. From the muon's perspective, so we are told, the actual distance between the muon and the detector will be contracted. The muon will thus experience itself to decay at a normal rate, but it will also perceive itself to be traveling across a physically shorter distance due to length contraction, and therefore the muon will nonetheless reach the detector and activate the bell despite decaying at a normal rate within its own frame of reference. But here again, the ontological incoherence of the theory undercuts this attempted resolution. Imagine that there is a second detector, which is connected to a second bell. Within this second detector are two atoms. If the two atoms are brought into contact with one another, the second detector will be activated and the second bell will ring. In attempting to explain the above paradox through length contraction, we must presume that the contraction of space from the muon's perspective is an actually real, physical effect, not merely a measurement distortion. If the distance between the muon and the detector only appears to be shortened, then this would have no bearing on the distance which the muon actually needs to cross in order to reach the detector. 10 meters is still 10 meters even if it only appears to be 5 due to my measurement distortions. There must be an actual shortening of the real physical distance in order for the muon to actually reach the detector in the same amount of time. So, if we take this length contraction to be a physically real, ontologically substantive reduction of spatial distance, then we would expect this contraction to bring the two atoms in the second detector into contact with one another, as the real distance between them will have decreased. The second detector will be activated and the second bell will ring, but only within the muon's frame of reference. There is no reciprocal contraction or dilation from our perspective which can bring the two atoms together. Within our frame of reference, the second bell will not ring, yet the ringing of a bell is a very real, physical event. Either the bells ring or they do not. Here then we can begin to see the fundamental problem which Henri Bergson saw within the Einsteinian framework. Insofar as STR is taken to be simply a measurement effect rather than an ontological effect, then the theory is able to maintain its relativistic symmetry, but is unable to explain any actual empirical effects. As soon as we begin treating these effects as physically real effects, however, this symmetry collapses and the theory dissolves into incoherence. If we treat the muon's hypothetically contracted length as a mere measurement effect, then the muon should not reach the detector from its own frame of reference because it will still need to cross the exact same distance in the same amount of time. The bell will ring within the Earth's reference frame, but not within the reference frame of the muon. If we treat this contraction as physically real, however, then the second bell will ring within the muon's reference frame, but not within the reference frame of the Earth. Either way, we have the same problem. As soon as we attempt to treat relativistic effects as physically real effects in order to explain empirical phenomena, the relativistic symmetry ruptures, and the theory produces contradictory predictions. Explaining the muon's behavior in terms of length contraction is no more than playing a shell game. It is an attempt to maintain relativistic reciprocity by treating time dilation as a merely perspectival effect while attempting to regard length contraction as physically real. Yet, if this length contraction is treated as physically real, then the reciprocity of the theory breaks down in the exact same way, but in a manner that is now obfuscated by the conceptual shell game. The theory can't have its cake and eat it too, and yet the theory can only explain empirical phenomena by attempting exactly that. In reality, the muon will in fact reach the detector in this scenario, and the atoms in the second detector will not ring the second bell. The muons really do seem to have longer lifespans at higher velocities, and this is a phenomenon which stands in need of explanation. Length contraction, on the other hand, cannot bring two objects into contact with one another because such contraction cannot be physically real. The muon's elongated decay time is an empirical fact which we can actually observe, and it is one which is very commonly explained by invoking special relativity. But, as we have begun to see, special relativity cannot explain any objectively real phenomena at all. It can only account for measurement distortions which are only real from a given frame of reference. The irony here is that the increased lifespan of muons is often presented as though it were actually evidence for the veracity of special relativity, when in reality this is a phenomenon which special relativity cannot actually account for at all. Another experiment which is often brought to bear in an attempt to validate Einsteinian spacetime is the Hafel-Keating experiment. Within this experiment, extremely high precision cesium beam clocks were synchronized and flown around the world in commercial airliners. What the experimenters found was that the airliner clocks lagged measurably behind those which were left behind on the ground. Yet, here again, we can see that the inherent symmetry of STR cannot explain this effect. We must presume that some frame of reference is privileged in relation to an absolute background in order to account for the time dilation as a real effect rather than as a purely perspectival distortion. Remember again our initial thought experiment involving the setup with the airship. When we tried to bring the two sets of clocks together to find out which clocks were actually in sync, what we found was that we were unable to determine which clocks were actually in sync with one another due to the lack of a privileged reference frame. If you took your clocks up to the airship, then they would appear to have become out of sync with one another, but they would be in sync again once you return to your original reference frame. The effects were seen to be perspectival, not ontological, as there is no absolute simultaneity within special relativity. If we actually take STR seriously enough to apply it consistently, then we have no explanation for the effect observed within the Hofeld-Keating experiment. The clocks on the airliner should have experienced no real ontological time dilation, as one could just as easily declare that the plane was stationary and that the Earth was in motion. The plane's clocks would appear to lag from the perspective of those on the ground, but then the clocks on the ground should appear to lag behind from the perspective of the moving plane. If the clocks were synchronized together in relation to the same reference frame, then the purely measurement-based time dilation effects should have canceled out when the plane landed and returned its clocks to their original reference frame, but this is not what the experiment showed us. Something must break the symmetry of special relativity in order to actually explain any empirical time dilation as an ontologically real effect, rather than as a mere measurement effect. This is where many will point to the general theory of relativity as a way to contend with these failings of special relativity. Within GTR, it is claimed that the fundamental reciprocity of special relativity is broken by the effects of acceleration. So, for example, it could be said that the acceleration of the muon rather than its velocity is absolute, not relative, and this is why the time dilation effects are real for both the muon and for other observers. But how can acceleration possibly be absolute if velocity is entirely relative, given that acceleration is a change in velocity? If the muon can declare itself to be at rest and that the Earth is in motion relative to it, then that would then imply that it is the Earth which is accelerating. Invoking acceleration through general relativity simply invalidates the fundamental principles of special relativity by implying that there is no genuine symmetry here. General relativity does indeed regard acceleration as absolute, not relative, but general relativity does not provide us with a theoretical reason which can actually justify doing so. If the acceleration of an entity is objectively real regardless of its reference frame, then this acceleration, this change in velocity, must be an alteration in relation to something objectively real. This problem is almost always simply ignored in discussions of general relativity and its supposed ability to rescue special relativity from itself. What we are told, if anything, is that acceleration can be absolute because it can be a change in relation to the rest of the universe. If a change in velocity can be absolutized in relation to the rest of the universe, then doesn't it seem that the phrase rest of the universe is now discretely performing the exact same function once performed by the Newtonian absolute spatial background? If acceleration is not defined in relation to such a background, then what else could the phrase the rest of the universe possibly refer to? Perhaps we could take this to imply that somehow the contents of the universe as a whole can constitute an absolute spatial background which performs essentially the same function as the Newtonian absolute space. Although this suggestion is quite certainly a dodge on the part of Einstein's adherents, there is more to be said of this idea, and so this notion is something that we will be returning to later on. For now, however, what is significant here is that general relativity contains no such theory, by which we could regard the contents of the universe as constituting a background through which acceleration could be regarded as objectively absolute. This idea is, for now, simply an ad hoc suggestion, which is invoked for the blatant purpose of obfuscating the actual shortcomings of Einsteinian cosmology. There is no theory of relativistic absolute acceleration, in other words, even though this idea of absolute relativistic acceleration is often used to resolve many paradoxes of special and general relativity, such as the twin paradox. But there are much deeper problems within the Einsteinian framework than even its inability to break its own symmetry in order to somehow maintain both explanatory power and conceptual coherence. Einstein's theoretical framework is ultimately one of pure metaphysical solipsism, and we can see this well-obfuscated fact by looking closely to another profound issue within the theories: the immeasurability of the one-way speed of light. It is exhaustingly reiterated that the speed of light is constant, and that we know this because we have, presumably, measured the speed of light in various ways and found that this speed is invariantly in keeping with the Einsteinian framework. What almost universally goes unspoken here is that the speed of light has actually never been measured because it cannot be measured even in principle, specifically due to the epistemological implications of special relativity itself. So let us first consider the conditions under which the speed of anything might be measured. You have a point A and a point B, and you have a bow which will fire an arrow from A to a target at B. Speed is, of course, distance over time, meaning that you need to know how far A is from B, and you then need a way to measure how long the arrow will take to arrive at B. So you need to synchronize two clocks, placing one at A and one at B. You stop the first clock when the arrow is fired, and then the second clock is stopped when the arrow arrives at the destination. You can then compare the two clocks, subtract the difference, and then compare the travel time with how far the arrow traveled. Achieving this with light, however, is much more problematic. There is no way to determine the speed of light without measuring the elapsed time, but the problem is now that there seems to be no way to actually synchronize two clocks in a way that actually accounts for the potential time dilation effects of special relativity. You can synchronize two clocks right next to each other at point A and then separate them, but then the clock that you move to point B will be subject to whatever time warping effects might have resulted from this motion. You can try to synchronize them at a distance using radio waves, but then that will require you to account for the time it takes those electromagnetic waves to travel, which is precisely the thing that you are trying to measure to begin with. If you continue thinking about the different ways that you might try to go about doing this, you will eventually realize that there simply is no way to measure the one-way speed of light that doesn't involve accounting for the effects of special relativity, which already presume to know what the one-way speed of light is. So how can we possibly claim to know that this speed is constant? It turns out that we can in fact measure the two-way speed of light by reflecting the light back to our starting point from its destination. This can actually work because in this scenario we only need one clock. Measured in this way, the combined outgoing and return speed of light does appear to be constant, or at least it does not appear to vary in relation to inertial frame. But that still leaves us with a very serious problem. How do we know that the speed of light is isotropic, having the same outgoing and return speeds, and not anisotropic, with different outgoing and return speeds? Most commentators on this problem tend to look at this issue as an engineering problem. They seem puzzled that there doesn't seem to be a way to measure the one-way speed of light that doesn't involve making circular presumptions. What these commentators often fail to realize is that this is not a practical problem at all, but rather an epistemological and metaphysical problem. The issue here is not that there is no practical way to synchronize the clocks you wish to place at points A and B. The problem is that within the framework of special relativity, there simply is no objective reality with regards to whether those clocks are synchronized or not. There will always be some possible frame of reference from which the clock ticks are exactly simultaneous, but that will always only ever be apparently the case from a particular vantage point. There will also always be innumerable other frames of reference from which the two clocks are out of sync. Due to the fact that there is no privileged frame of reference within special relativity, this means that there is no objective truth with regards to whether the clocks are actually synchronized, no matter how you go about trying to sync them. Einstein himself commented on this problem, and his commentary is very revealing here. Einstein states that we can simply define the speed of light as being isotropic as a kind of convention. Einstein thus essentially tells us that he is simply declaring the speed of light to be isotropic, and therefore that the one-way speed of light is constant by definition. Now, of course, this seems like utter madness. I cannot simply declare the speed of my arrow to be a certain speed. The arrow has a real, objective speed, and whatever speed I declare is simply either true or false. Physical properties of real entities within the natural world should not be the kind of thing which we can establish by appeal to convention. This madness does not come about because nature is unimaginably bizarre. It comes about because it is here that we can clearly see the manner in which the Einsteinian serpent comes to devour its own tail. The foundational premise of relativity is that the speed of light is invariant in relation to inertial reference frames, but the very notion of speed itself as an objective property necessarily presumes absolute objective simultaneity. If there can be no objective reality with regards to the temporal relationship between events A and B, then there can be no objective truth pertaining to how quickly or slowly event B succeeded event A, and thus no objective reality to speed at all. Einstein can state that he is permitted to define the one-way speed of light as constant as a matter of convention because he has realized that if we take the epistemological implications of special relativity seriously, then we are forced to conclude that there really is no objective one-way speed of light at all. The problem isn't a lack of information on the part of human beings or a technical limitation. There simply is no one-way speed of light to measure at all to begin with. So let us take a moment to consider just how absolutely shattering this conclusion actually is. If the isotropy of the speed of light is ultimately no more than an agreed-upon social construct, then this implies that special relativity itself, and all empirical inferences which presume the veracity of special relativity, are themselves no more than social conventions. First of all, we can begin by looking at the infamous Michelson-Morley experiment with which our journey began. If the speed of light is regarded as anisotropic, then this would imply relative motion in relation to an etheric background, even despite the null result. Similarly, gravitational wave detectors utilize laser beam splitters and mirrors which recombine the beams in a manner very similar to the Michelson-Morley experiment. If we regard light as anisotropic, then interpretations of the data collected by these gravitational wave detectors would be drastically altered. Many empirical inferences made within practical physics also presume the isotropy of light. Anisotropic light would have massive implications for particle physics, as it would imply that particles might behave in very different ways depending upon their direction of motion. Keep in mind here the way that I am using the term regard within this context. As we have already seen, this is not a matter of whether or not light is actually isotropic or anisotropic. There is no fact of the matter either way. As Einstein himself tells us, we can simply choose to regard light as isotropic in order to simplify our models, but this would simply be a convention. The point here is not that light actually is or even could be anisotropic. The point is that if we actually apply special relativity consistently, we are forced to conclude that all of the empirical inferences above are in fact no more than phantoms. These inferences presume an objective ontological reality which is not actually there within special relativity. If there simply is no truth to the matter with regards to whether or not light is isotropic, then this necessarily implies that there really is no truth to the matter with regards to whether the results of gravitational wave detectors are actually valid. There is likewise no truth to the matter as to whether particles behave in different ways depending upon their direction of motion, and there is no truth to the matter with regards to whether the results of the Michelson-Morley experiments were actually null or just apparently null. In addition to the fact that STR negates the very foundations of its own theoretical structure, and the fact that the theory plays a smoke and mirrors game with the ambiguity between ontological effects and measurement effects, special relativity also manages to obfuscate the distinction between phenomena which supposedly offer empirical support to the theory and phenomena which are in fact only phantoms of the theory's own ambiguity. The phenomenon of length contraction, for example, is often claimed to be a physically real ontological effect. It is claimed that objects really do contract due to high velocities, and that this is an empirical reality which is explained by STR. But this is yet another alleged phenomenon which has never been empirically verified to be physically real. And moreover, it cannot be verified to be physically real due to the epistemological limitations imposed by the theory itself. Any measurement device used in an attempt to confirm the veracity of length contraction will itself be affected by the very contraction which the instrument would be intended to measure. Unlike the Lorentzian contraction discussed previously, the length contraction postulated by STR is not theorized to be a physical compression of actual atoms and molecules which make up physical bodies. Rather, it is a contraction of space itself. Even if one were to get in a spacecraft and travel at near light speed, one would not actually experience this alleged contraction as a perceptible effect. There would still be just as much space in between the molecules in your body, but this space would itself be smaller in relation to non-contracted space outside of your frame of reference. Nothing would appear to be amiss from your perspective within the ship. Or at least this is one interpretation. Academic physicists often seem perfectly content to treat length contraction as a purely relative effect in some scenarios, while regarding it as a very much physically real phenomenon in others, depending of course on what happens to be convenient. Within particle accelerators, for example, it is said that the effects of length contraction upon accelerated particles result in higher densities of such particles, thus increasing the likelihood of collisions. Similarly, it is said that accelerated atomic nuclei become physically more dense due to length contraction and thus result in more extreme nuclear interactions. As we can see, length contraction, as with all phenomena postulated by STR, is exactly as physical or merely metric as physics deems necessary in order to craft its narratives. Special relativity is not a scientific theory. It is a shell game. It is often claimed that there are no empirical observations which have ever contradicted the theory of special relativity. But can this really be said of a theory which is essentially defining itself as true? Moving on to general relativity, then, the problems are only compounded by the attempt to use this relativistic framework in order to account for gravity through the notion of space-time curvature. As we have already seen, the fundamental Newtonian insight regarding the treatment of straight-line trajectories as states of rest provided the means for Newton to formulate gravity as a force which acted to bend the resting straight-line trajectories into elliptical orbits. The fundamental insight of general relativity, then, was to maintain this notion of resting straight line trajectories while discarding the notion of absolute stationary rest and seemingly overcoming the need to conceptualize gravity as a force which acted at a distance without any apparent medium. This was achieved through generalizing the space-time deformation which special relativity seemingly made possible, though, as we have already seen, treating such deformation as ontological already necessitates conceptual incoherence. General relativity conjectures that gravitational effects are due to the deformation of spacetime due to the influence of mass or energy. Einstein came to believe that the mutability of space implied by special relativity could imply a dynamic, fluid-like spacetime. Gravitational effects could then be regarded as the result of physical bodies traveling in straight-line, resting trajectories through a curved spacetime topography, which was quite literally stretched out by massive objects. The physics community, however, seems to experience a rather severe difficulty in coming to a coherent agreement as to how exactly this hypothetical spacetime curvature is meant to actually result in the physical effects of gravity. On the face of it, this spacetime curvature would seem to operate in a rather straightforward manner. Physical bodies are attempting to follow straight-line trajectories with fixed velocities because such trajectories are a kind of resting state. Due to the curvature of space itself, these technically straight trajectories appear as elliptical orbits. This explanation, however, doesn't quite do the work that's needed. This explanation can account for the curvature of otherwise straight trajectories through space, but this explanation can't actually account for what the real phenomenon of gravity actually does. Imagine, for example, that an apple is floating in space above the Earth. The apple has no relative motion in relation to the Earth. Both objects are stationary in relation to each other, and there is no absolute motion which can prevent us from treating them both as such. If relativistic gravity can only account for the bending of trajectories through space, then we would expect this apple to simply stay where it is. There is no trajectory to be bent by the curvature of spacetime. This explanation would imply that the force of gravity was always a modification of one's relative velocity in relation to the gravitational influence. Things which are moving faster would be pulled down harder towards the Earth because of the modification of their own inertia. Objects with less relative velocity in relation to the Earth would experience less gravity. Obviously, this is not what we find in the real world. Another very common explanation for relativistic gravity is through the invocation of gravitational time dilation. This narrative proposes that the effects of gravity are actually due to the asymmetry of time dilation, which would affect bodies moving through gravitational fields. As an object passes through the gravitational field, the part of the object that is closer to the source of gravitational influence will experience more time dilation. Its internal clock will tick more slowly, as it were, in relation to the side of the object which is further away from the gravitational source. This effect would then result in a kind of torque, which would tilt the object in the direction of the gravitational influence, thus resulting in the apparent gravitational attraction. The problem with this explanation is that it blatantly contradicts the equivalence principle of general relativity. Within GR, the equivalence principle states that there is no objective distinction between apparent gravitational attraction due to mass and apparent gravitational attraction due to acceleration. If you are in a spacecraft traveling at a constant acceleration, then you will experience apparent gravitational pull towards the back of your spacecraft. Moreover, you will also experience the entire universe as affected by time dilation in relation to this apparent gravity. Clocks in front of you will tick faster, and those further out from you will tick faster still, at least from your perspective. But this time dilation is observer dependent. You will not actually cause gravitational attraction through the rest of the universe due to a temporal torque resulting from the fact that you will perceive the clocks of other observers to be ticking at different rates. This is necessarily a measurement effect, not an ontological effect. Due to the equivalence principle, however, we can see that time dilation due to the effects of mass cannot cause gravitational effects either, as the time dilation produced by massive bodies like the Earth will also be observer-dependent measurement effects, not physical effects. Does it really seem like the apparent force holding you down to your seat right now is due to the fact that time is passing at an infinitesimally faster rate for your head than for your legs? Throw a basketball straight up into the air and then watch it fall. How could we possibly explain the ball's attraction towards the ground with the idea that time is passing more rapidly at the top of the ball than the bottom of the ball? Moreover, this explanation fails once again due to the inherent symmetry of relativity. The ball is undergoing time dilation from your perspective on the ground, but the ball experiences no such time dilation within its own frame of reference. From the ball's perspective, its own internal clocks are ticking in the exact same way that they always do, and it is your clocks which are ticking differently. Neither your frame of reference nor the ball's is privileged, and thus these effects cannot result in real, physical gravitational effects which must be equally real, irrespectively of differences between inertial reference frames. The third explanation, which seems to have been Einstein's own interpretation, is that gravitation due to massive objects quite literally is accelerative gravity. That the basketball falls down to the Earth because the Earth is literally accelerating outwards in all directions. Now, this would intuitively seem to be completely absurd. If the surface of the Earth were accelerating up towards the ball, then the Earth would presumably explode apart in all directions. This acceleration, however, is said to be due to the fact that space is not merely deformed by massive objects, but rather that space is in fact a kind of quasi-fluid, which is literally flowing into the Earth's center of mass. The Earth doesn't fly apart because this acceleration is caused by the fact that the Earth acts as a kind of sink, which creates a sort of four-dimensional space-time waterfall. You're being held down to your seat because space is moving downwards through you and into the Earth, and thus the acceleration caused by the Earth's gravity is quite literally the exact same accelerative force which pulled you backwards within your accelerating spacecraft. On a purely intuitive level, we can already see that this is an utterly fantastical and empirically unverifiable flight of imagination, and one which is self-defeating in much the same manner we saw with special relativity. Einstein's theories of relativity were meant to absolve the luminiferous ether and, by extension, Newtonian absolute space by relativizing space and time. There was seemingly no longer any need to postulate an unobservable background of static space or ether, such that space could simply be regarded in a relational manner as Leibniz and others had argued, rather than as a medium in itself. But here we can see that in attempting to fully generalize this account, Einstein not only reintroduces space as a medium, but also refashions space into something even more fantastical than it ever could have been within the Newtonian or etheric frameworks. On the one hand, Einstein purports to treat space as though it were nothing but pure potentiality, as many philosophers have argued, that the word space really just refers to relations between the coordinate properties of real objects within the natural world. This treatment is absolutely crucial for the conceptual coherence of special relativity, as the theory requires that all inertial reference frames be treated as equal. If we reintroduce an ontologically substantive notion of space, then the claim that all inertial reference frames are equal is invalidated. If space is an entity in itself with its own topography, then it follows that objects can in fact be objectively in motion or stationary in relation to that spatial background. But with general relativity, Einstein does in fact reify space in exactly this way. Space is now regarded not only as an ontologically substantive background, but also as a fluid medium which can literally flow into centers of mass. This also requires the introduction of a fourth spatial dimension. Many physicists would ardently deny this because their equations don't explicitly designate such a fourth direction. Such physicists seem to believe that their equations literally are reality rather than scientific models, and therefore that they have no obligation to actually account for any ontological implications which are hidden within those equations. Nonetheless, we can see that this is absolutely necessary ontologically. In order for space to be bent in the manner indicated by general relativity, it has to be bent into something. As we have already seen, claiming that the fourth dimension is actually time just does not work. In order to fold a two-dimensional piece of paper, you need a third dimension into which the plane of the paper can be deformed. In order to bend three-dimensional space, you need a fourth direction that you cannot point in. But now consider the fact that the gravitational force must be regarded as an acceleration within this context. What this then means is that the space which is flowing down through you right now in order to hold you to your chair cannot be a flow with a constant velocity. If it were, then obviously there would be no experience of acceleration, as there is no real distinction between stationary rest and constant velocity within this framework. Only increasing velocity results in a feeling of acceleration. In other words, the space which is flowing through us and into the Earth's center of mass must be flowing faster with each passing moment. The speed of the flow of space must itself be constantly increasing incessantly in order for the deformation of space to actually account for gravity. This introduces yet another paradox. If space is a real entity with real properties which can be altered, then this alteration must be due to energy. The Einsteinian framework tells us that mass and energy are interchangeable and therefore provides a means by which a massive object can cause the deformation of space, but it doesn't give us a means by which a massive object could accelerate this deformation. If the flow of space into the Earth must be happening faster and faster with each passing moment rather than flowing at a static velocity, then where is the energy coming from to fuel this endless acceleration of spacetime? Is the mass of every object in the universe increasing with each passing moment in order to allow for this constantly intensifying deformation? Moreover, if we are to regard space as flowing into centers of mass, as the theory seems to imply, then where does this space then go? Is it simply annihilated once it reaches the center of mass? This is not simply a pedantic question. If we are going to treat space as an entity in itself with real properties, then we cannot simply hand-wave away questions about the implied ontological status of space. Yet the Einsteinian framework tries to have its cake and eat it too by treating space as though it were a kind of matter or actual entity with real properties, while simultaneously exempting it from any of the restraints which we presume to condition real matter in the real world. And it is here that we can begin to see that beneath this entire tangled maelstrom of inconsistencies, the true failure of the Einsteinian framework is that in reality it doesn't actually offer us an explanation of anything at all. Einstein does not give us any explanation as to how or why space would be the kind of thing that would have such properties in the first place. All he gives us are equations which purport to describe these supposed processes. If we are going to regard space as something which can bend and flow, then there needs to be some sort of causal explanation here which explains why space is more than a mere distribution of strictly potential geometric relationships. Yet general relativity gives us no such thing. Einstein himself eventually realized that this conclusion was inevitable, and in 1920 he delivered a public presentation at the University of Leiden called Aether and Relativity, in which he himself concluded that the endowment of space with these properties necessarily implied that space was more than mere space, but rather that space had to consist in some sort of etheric medium. But Einstein's theories provide us with no such medium, and neither do any of the other fields of physics. When we look at the various quantum fields which are said to permeate our cosmos, we find that none of them possess the properties which a relativistic ether would need to have in order to actually account for the properties which Einstein attempted to attribute to spacetime. Einstein's theories, therefore, do not actually constitute a scientific explanation, but rather the promise of a potential explanation which has yet to ever materialize. Academic physicists seem to believe that none of these considerations are truly relevant, as long as the mathematical equations work. But this would be to stretch the definition of working far beyond its breaking point. Mathematical equations do not move celestial bodies, nor do they hold one's shoes to the ground. Gravitational phenomena are real phenomena in the real world, which are described with mathematical equations, which are created by human beings as descriptive tools. Isaac Newton did not believe that his equations moved the planets around the sun. His equations accounted for gravitational effects, but did not actually explain them, and Newton himself was explicitly aware of this. Newton famously claimed that he had no pretensions of providing a genuine scientific explanation for the actual causes of gravity. Because gravitational influences seem to operate at a distance with no apparent medium, Newton believed that the cause of gravity could not be physical at all, and therefore that there could not actually be a scientific explanation for gravity, but only a mathematical description. Newton surmised that gravity was actually driven by a divine, spiritual force rather than a physical one, and therefore driven by a force which lay beyond the scope of scientific naturalism. As we shall see in future videos, although Newton was quite correct in seeing that the cause of gravity could not be physical, he was quite wrong in suggesting that this left an explanation for gravity beyond the bounds of scientific naturalism. Science can and must account for the non-physical, and in fact it has already been doing so unwittingly since at least the 19th century. Nonetheless, Newton was able to make this very clear, as Newton was not an adherent of the mathematical materialism which would later come into vogue, and therefore Newton saw no issue whatsoever with the suggestion that certain physical phenomena have non-physical causes. Unlike Newton, however, who was very honest about the fact that his theories did not actually explain gravity, Einsteinian physics instead is presented as though it were a genuine explanation, while hiding the fact that it is not within an endless conceptual shell game. One common myth about relativity, which all of us have probably heard at some point or another, is that relativity implies a physically inviolable speed limit on the universe. Nothing can have a velocity faster than the speed of light, so we are told, because of the way that mass comes to be exponentially amplified at relativistic velocities. More mass requires more energy to accelerate, and we are told that due to the relativistic amplification of mass, the energy required for further acceleration approaches infinity as an object approaches the speed of light. The problem with this claim, yet again, is that it completely ignores the fundamental symmetry of relativity itself. The relativistic mass of a high-velocity object cannot be ontological but only perspectival. As we have already seen, relativity presumes that any object which is moving at a constant velocity is literally at rest in relation to its own inertial frame of reference. Relativistic mass can therefore only be an apparent increase in mass, which is only real from the perspective of an external observer. From the reference frame of the object itself, its mass will remain exactly the same, and therefore there will be no increase in the amount of energy needed to accelerate the object further. If we actually take the relativism of Einstein's theories seriously, what they imply is that accelerating an object from 99.9999% of light speed to 100.0001% of light speed should require the exact same amount of energy as that required to accelerate an object from 0% of light speed to 0.002% of light speed. This is because, given the basic premises of relativity itself, there is no way that the laws of physics could distinguish between those two situations. If one does a bit of digging into this issue, what you will find is that physicists themselves will admit that this notion of light speed enforcement by relativistic mass is actually a myth. Rather, they will instead tell us that nothing can move faster than the speed of light, because if something were to move faster than the speed of light, then that object would, according to relativity, begin moving backwards in time. This would break the universe, so we are told, but of course this is obviously absurd. Nothing can break the universe. Faster than light causation would, however, break the causal structure of Einstein's theories. Certain forms of hypothetical exotic technologies like wormholes, Alcubierre drives, and quantum telegrams have been suggested as ways in which faster-than-light travel might be theoretically possible. Physicists will insist that these exotic technologies must be practically unfeasible, even if relativity itself presents us with such loopholes, as doing so would break the universe. But consider this carefully for a moment. Even if these theoretical technologies are not practically possible, doesn't it seem that there is something deeply amiss that a logical impossibility should only be practically unfeasible? Doesn't there seem to be something very confused about the notion that the nature of the universe itself would allow for loopholes which would break its own logical structure, but then create ad hoc practical limitations to prevent those loopholes from being exploited? On an intuitive level, we can clearly see the implication that the basic structure of the Einsteinian universe is not logically coherent. Yet modern physics has made an art form of insisting to us that such intuitions cannot be trusted, that the universe is just too spooky for our stupid monkey brains to understand, and therefore that physics has no obligation to actually be self-consistent. This ideology is deeply unscientific. When we look to the greatest minds throughout the history of science, we find no such absurdity. Thinkers like Aristotle, Newton, Goethe, Galileo, Maxwell, and innumerable others were thinkers who were compelled specifically by the conviction that nature is in fact comprehensible. If the human mind is in fact a product of nature, then this of course implies that the basic compositional features of the human mind should be the same basic compositional features of nature itself. We expect nature to be elegant and conceptually coherent. We expect to see that nature takes very simple principles and then elaborates them in consistent ways. We expect nature to embody the aesthetics of symmetry, parsimony, and self-similarity, not because of peculiar, idiosyncratic flukes of human cognition, but because human cognition is nature in the exact same way that plants, animals, stars, and crystals are nature. Insofar as we abandon this conviction that nature is consistent with human cognition, we are abandoning the very project of science itself. But perhaps even more damning for general relativity is the fact that it does not actually account for the empirical reality we find in nature. Even from the time of its origins, general relativity never accurately accorded with the morphology and behaviors of galaxies and intergalactic structures. The effects of gravity predicted by the theory were always far too weak to actually account for how galaxies and intergalactic structures are able to maintain themselves. If general relativity was correct, then we would expect galaxies to tear themselves apart, as there is not nearly enough matter within galaxies to actually account for their formation or self-perpetuation. In order to account for this incongruity, the astrophysics community has confidently declared that some 85% of our observable universe must consist of so-called dark matter. This dark matter is a purely ad hoc hypothesis which is postulated for no other reason than to bring general relativity back into accordance with observation. Of course, it is not uncommon for science to postulate phenomena which are not directly observed. If I go outside and see that the ground is wet, then it is perfectly reasonable to conclude that rain must have occurred even if I did not observe the rain itself. Rain, however, is a known phenomenon. We have plenty of reason for believing that rain is a real thing, and so we are not conjuring the notion of rain out of thin air for the specific purpose of explaining this particular observation that the ground is wet. Dark matter, however, is conjectured specifically due to the inability of general relativity to actually accord with the phenomenon which it is meant to explain. Even modern particle physics, with its motley ensemble of exotic and often unobservable entities, provides us with no candidates for this supposed dark matter. Each time, particle physics has produced a modified theory which has included potential dark matter candidates, such modified theories have failed to make accurate predictions. Rather than questioning the validity of general relativity itself, the academic physics community has instead developed ever more exotic notions of dark matter, which are ever more massive and ever more weakly interacting. More massive particles are said to be more difficult to produce through particle collisions, and thus, by increasing the presumed mass of dark matter particles, physics is able to continue pushing dark matter just beyond the range of what can be falsified experimentally. The mathematical tools of general relativity can indeed make accurate predictions for a small range of observations, but most people don't seem to realize how small that range actually is. In addition to an inability to account for galactic observations, general relativity also fails to accord with observations even within our own solar system. General relativity seems to account for the precessions of the major planetary bodies of our solar system, but the theory quickly breaks down once we begin looking to the behaviors of trans-Neptunian objects. The clustering behaviors of objects within the Kuiper belt imply far more gravitational influence than what general relativity would predict given the masses involved. Orbital perturbations of such objects likewise cannot be accounted for by the gravitational influences of the known planets. Much as with so-called dark matter, academic physics has engaged with these incongruities by postulating an exotic, unobservable entity rather than subjecting their preferred theory to serious scrutiny. In order to bring these observations into accordance with general relativity, astrophysics has declared the existence of an unseen Planet X. In order for this Planet X to actually account for the observational anomalies which it has been invoked to account for, this planet would need to be a gas giant with a mass comparable to that of Neptune or Uranus, if not significantly larger. It would also need to have an immensely eccentric orbit, which is also sharply inclined in deviation from the solar plane. If such a planet does exist, then this of course begs the question of why astronomers cannot seem to find it. But even if such a planet were discovered, then its very existence would be extremely difficult to explain within our current models of solar system formation, models which are, of course, built upon the foundation which is general relativity theory. Taken together or separately, special and general relativity are a conceptual train wreck. Oftentimes, this incoherence is obfuscated by a kind of smoke and mirrors game in which it is suggested that this isn't actual conceptual incoherence, but rather a result of the fact that nature itself is mind-bendingly bizarre, mathematically convoluted, and counterintuitive. When confronted with the blatant contradictions and failures of these theories, the academic physics community proceeds to suggest that its critics are missing some arcane subtleties hidden within the mathematics which only the fully initiated can properly understand. Yet, when we question those fully initiated hierophants about these problems, they don't have any straight answers either, and they proceed to either hand-wave these issues entirely or produce their own idiosyncratic reframings as though they were the gospel truth which is actually presented by the theories themselves. Modern academic physics, despite its ostensive materialism and secularism, has become guilty of all the same crimes which those materialists accuse spiritual and religious traditions of participating in. Intentional obfuscation, deference to unknowable mysteries, appeals to authority, disregard for empirical observation, and oftentimes outright gaslighting. When confronted with these critiques, physicists will often declare that even though these theories certainly have glaring problems, there is no real alternative. We don't have a better theory, and therefore we cannot abandon the Einsteinian framework until we do. If you think the Einsteinian framework is bad, they suggest, then why don't you come up with a better theory? This, if you are wondering, is exactly what I mean by gaslighting. Let's say that you are serving on a jury for a murder case. The working hypothesis is that Bob killed Steve. The prosecution makes their case that Bob did in fact kill Steve because Bob was the only person known to be on the same floor of the hotel which Steve was murdered in on the night he was killed. Yet Bob is an elderly, wheelchair-bound man with no criminal record and no connection to Steve. Moreover, there is surveillance footage which clearly demonstrates that Bob was asleep in his hotel room when Steve was killed. It seems rather clear that whatever happened to Steve, it was not Bob who killed him. The prosecution then makes a very strange argument. They say that there is not yet any better theory as to what happened to Steve. They insinuate that if the defense wants to exonerate Bob, then they need to produce a better theory, or otherwise there is no choice but to proceed as though Bob killed Steve, and thus convict him of murder unless a better theory is produced. This argument is, of course, patently ridiculous. The rational conclusion to draw here is obviously that we do not actually know what happened to Steve, and thus cannot prosecute anyone until further notice. It is absolute nonsense to suggest that a demonstrably false theory is better than no theory. Admitting no theory means acknowledging the real limits on what we can and cannot be certain about, and being fully transparent about where the gaps in our knowledge actually are. Acting as though a demonstrably false theory is correct in absence of a better one is pure, unequivocal, and I would argue blatantly intentional obfuscation. What this gaslighting tactic obfuscates, beyond the blatant failures of the theories themselves, is the fact that academic physics does not have a better theory because academic physics has made no attempt whatsoever to produce a better theory. For nearly a century, relativity has been considered an established fact within physical science. Attempts to produce alternative explanations have been consistently met with ridicule, and those academics who have dared to suggest that Einstein was wrong have been ostracized as fringe lunatics and crackpots. All attempts to produce a theory of quantum gravity, and by extension string theory or membrane theory, have presumed that any attempt at such a theory of everything must necessarily preserve the structure of the Einsteinian framework if it is to be subsumed into a more general quantum framework. As yet, all such attempts have failed, and will continue to fail insofar as they continue to cling to the notion that exotic, arcane mathematics can be substituted for empirical reality in order to graft the corpse of relativity onto quantum field theory. I am certainly not the only person to have leveled such criticisms against Einsteinian cosmology, but my true aim here is not simply to demolish established dogmas. My aim is rather to lay the preliminary foundations for a more genuine and cohesive understanding of nature. I am certainly not the first to attempt the development of a truly post-Einsteinian understanding of physical nature. Frameworks such as variable speed of light models, electric universe theories, and plasma cosmologies have also attempted to resolve these issues. Much like Einsteinian theories, which these frameworks attempt to supersede, however, models like the electric universe theory and plasma cosmology tend to suffer from the very same conceptual inadequacies which plagued the Einsteinian understanding of nature. Although often immensely courageous and ambitious, these frameworks largely fail to move beyond mechanistic materialism, and therefore find themselves engaged in the intrinsically Sisyphean and futile attempt to understand the conditions of physicality in purely physical terms. The ground of the physical world itself is not, and necessarily cannot be, physical. As stated previously, the central problems which we have encountered here are not mathematical or technical problems. They are conceptual problems. And thus, before attempting to directly contend with the phenomena discussed above, we must first ensure that we are not crippled by the same conceptual deficiency which asphyxiated the 20th century science which struggled to grow beyond those bounds. In order to do so, we will begin the next installment of this series by looking at metaphysical frameworks which were developed specifically to transcend these limitations. Ideas which were developed by two of Einstein's most significant critics, Alfred North Whitehead and Henri Bergson. We will then begin to use these ideas to reevaluate our understanding of nature by bringing these process metaphysical models of Whitehead and Bergson into contact with the very mystery which Einsteinian cosmology had initially set itself to unveil: the nature of electromagnetism. Thanks for watching.